All right, in this video we're going to look at computing the average value of a function throughout a certain region. So to illustrate, let's say we have a function f of xy, and this denotes the temperature at the point xy. Okay, and so if we want to find the average temperature across, say, this rectangular region R, okay, one way to approach this is to think about just sampling a whole bunch of temperatures throughout the region and then just taking a straight average of those temperatures. Okay, so in other words, just add all of those temperature readings up and then divide by the number of readings that you have. Okay, so to do this, let's go ahead and partition this rectangle into a bunch of sub-rectangles. And within each subrectangle, I'm just going to select a point and measure its temperature at that point. And as long as my subrectangle is not too large, okay, that temperature reading should be a pretty good representative of the temperature throughout this entire subrectangle. Okay, so here we'll say that the average temperature, and we'll denote this as F bar here, would at least approximately equal, okay, the sum of all these various sample temperatures. And I'm just using that same labeling that we used in defining the double integral. So like x1 star, y1 star, this is just going to be some point I select in this rectangle here, say up in the upper left-hand corner. Then I move over and I select another point and measure its temperature there, and then so on and so forth, right, throughout all those separate rectangles. So here I'm just summing up all of those temperature readings, and then I'm going to divide that by the number of readings I have. And if I divide this interval here along the x-axis that goes from A to B into n subdivisions, and then I use m subdivisions for this interval along the y-axis, then there's going to be a total of n times m subrectangles. So in other words, n times m total temperature readings. Okay, so again, I'm just adding up my temperature readings and dividing by n times m, the number of readings. Now we can go ahead and write that numerator using sigma notation, but since we are now summing across the x and the y directions, there's really going to be two summations. Think about adding across each of the columns, and then you're going to go row by row doing that. So you're going to get really a double sum here. And I just put the 1 over nm out front. Okay. And now, since this thing is starting to look pretty similar to that expression we saw in the definition of the double integral, then what I'm going to do is put a little delta x times delta y out here, and then I'm going to correct for it by putting the delta x delta y down here. So I'm really just multiplying by 1. But by doing this now, this expression here, starting with these sigmas, this is the Riemann sum approximation to the double integral of our function f over the rectangle R. And then I have some of this, this clutter stuff out front. Okay, so what exactly is this thing out front equal to? Well, notice that if I call the width of my partition for the x-axis delta x, and that would just be b minus a, the length of the interval, divided by n, the number of subdivisions, and I call delta y the width of this for my partition of the y-axis, and that would just be d minus c over m. Replacing delta x and delta y with those expressions, notice the nm is going to cancel with this nm, and then that's going to leave me with this product, b minus a times d minus c, and that's nothing other than the width times the height of this rectangle, and so that's simply the area of the rectangle. So now in the next line, right, this thing is just equal to 1 over the area times 1 over the area of the rectangle times this Riemann sum approximation for the double integral of our function. Okay, and now lastly, this approximation to our average temperature is going to get better and better if I use more and more sample temperatures, right? So in other words, if I let the number of subdivisions get infinitely large, right, then this approximation is going to approach the true average and ultimately will converge to it if I take a limit. So the last thing we're going to do here is take that limit as we let the number of subdivisions n and m approach infinity. And then this Riemann sum here is going to converge to the double integral really by its definition, and we still have that 1 over the area. Okay, so in conclusion, to compute the average value of a function over, say, a region R, you just compute its double integral and then divide that double integral by the area of your region. All right, and that's going to do it. We'll see this all in action in the next video.